Welcome to the deep dive. Today we're digging into something pretty revolutionary happening with supercomputers. Now, when I say supercomputers, think, the absolute biggest machines out there, the ones predicting climate change or helping find new medicines. They call them high-performance computing systems, or HPC. But the tricky part, getting software installed and working correctly on them, it's traditionally been this massive, slow, manual job. Really a headache, honestly, and lots of room for error.
That's exactly right. And the paper we're looking at today aims straight at that problem. Its title is a bit technical: Automating HPC Software Compilation, Deployment, and Error Resolution Through an LLM-based Multi-Agent System. But basically, it's about using cutting-edge AI, specifically large language models, or LLMs, to fix this huge bottleneck, making these supercomputers, well, easier to actually use.
Okay, AI stepping in. So the idea is what? That a team of AIs can actually build, install, and maybe even fix software problems on these machines. That sounds ambitious.
It is, and they're showing some pretty remarkable success.
So let's explore that. You might be sitting there thinking, okay, AI, supercomputers. Why is this software thing such a big deal? Well, the why is key. Right now, it's mostly people doing this work by hand. Imagine, like, building a super complicated Lego castle, but you've got no instructions. Just a giant bin of bricks. And every single piece has to be perfect. Get one wrong, and maybe the whole thing falls apart or just doesn't work right. It causes huge delays in really important science.
Exactly. It's slow, it's error-prone. So the paper proposes using an LLM-based multi-agent system. Think of LLMs, large language models, like really advanced chatbots. Maybe you've used ChatGPT or something similar. But instead of just chatting, these are trained to understand and generate computer-coded instructions.
Okay, smart chatbots doing code.
Yeah.
And the multi-agent part.
That just means it's a team of these AI helpers, each maybe with a slightly different job. So, for example, they have one AI called the generator. Think of that as the builder. It creates the first draft of the installation instructions, the build scripts. Then there's another AI, the reviewer. That one acts like an inspector, checking the generator's work for mistakes or ways to make it better.
Ah, okay. So like a builder and an inspector working together, that makes sense. What happens if, the inspector finds a problem or if something just breaks during the installation?
That's actually the clever part. If there's a failure, a build failure, they call it the error message, gets fed right back to the AI team.
Oh, interesting.
Yeah. They analyze the error, figure out what went wrong, and then they learn from it. They adjust their approach and try again. And they're persistent. They can make up to 10 attempts to get the software built correctly.
Wow. Okay. 10 tries. Do they actually succeed often?
The results were genuinely impressive. Overall, the system managed a 97% success rate.
97%.
Yep. Across over 100 common HPC software packages, things like Python, CUDA, really essential tools. And they tested a whole range of LLMs, too. The big commercial ones like GPT-4 and Claude 3, but also several open source models.
Okay, 97% is huge.
Yeah.
What else did they find? Because you mentioned different AI models.
Right. So the experiment showed some really interesting things. If the AI only got one shot, one attempt, the closed source models like GPT-4 and Claude 3 did much better. GPT-4 got it right about 55% of the time, Claude 3 around 40%. The open source ones really struggled on the first try, like single digits mostly.
Okay, so the commercial ones were better out of the box.
Initially, yes. But here's where it gets really interesting. When they allowed the AIs to have multiple attempts to self-correct based on those error messages.
The learning part.
Exactly.
Yeah.
All the models improved dramatically. Claude 3 repair, they called it, hit a 90% success rate. GPT-4 repair got over 88%. That feedback loop makes a massive difference.
So learning from mistakes is key. That makes sense.
It really is. And the absolute best performance, the real aha moment, it came when they combined two different self-correcting AI agents, like pairing GPT-4 with Claude 3 repair.
Like a tag team.
Kind of, yeah. That combo hit an astounding 98.04% success rate. It just shows that putting different AI minds together, leveraging their different strengths, can lead to even better results. It's like building an AI dream team for this specific problem.
98%, that's almost perfect.
It's incredibly high for such a complex task. And if you think about the bigger picture, what this means, Automating these really fiddly, time-consuming tasks frees up the human experts, the HPC admins, and the scientists. They don't have to wrestle with installations as much.
That they can focus on the actual research.
Precisely. It means faster science, faster drug discovery, better climate models, quicker materials design. Because that human bottleneck, the software setup part, gets significantly reduced. It shifts the focus back to the actual computing power.
So, okay, tying this back to you listening, what does this mean? Well, it's a huge step towards making all that complex science, the stuff running on supercomputers, more efficient, which indirectly helps speed up those breakthroughs we all benefit from in medicine, climate science, you name it.
Definitely. But there's always another side, right? While this automation is incredibly powerful, the paper itself brings up an important point: security. When you have AI writing and installing code on these critical systems, how do you absolutely guarantee it's not accidentally creating new subtle security holes? Vulnerabilities that maybe a human wouldn't make, or at least might spot.
That's a really crucial question.
It is. And it leads to thinking about the future roles for people. It's probably not about humans doing less, but doing different things. Maybe shifting from manually fixing build errors to designing the safety checks and guardrails for these powerful AI systems. Something to definitely think about.